This is problem 249. As you can read here, it's a two-dimensional steady-state conduction occurs in a hollow cylindrical rod of thermal conductivity K, 16 watts per meter Kelvin, an outer radius of 1 meter, and an overall length of 5 meters, where the origin of the coordinate system is located at the midpoint of the center line. So let's start by drawing this out, just a quick schematic here. Here's our hollow cylindrical rod. This has a length of 2z0, and we have an outer radius and an inner radius. So because of the diagram here, let me draw an end view, r sub I, and an outer radius here, r sub O. And then we'll also draw a side view where the coordinate system is placed such that z equals 0 at the center of the rod. So z equals 0, or z0 on both sides there, like so. Notice also that it says this is steady state conduction, so we'll keep that into account later on. The inner surface of the cylinder is insulated, which means that along this surface here, it's insulated, so the heat flux is going to equal to 0. And here we're going to distinguish, since this is a 2D problem, we're going to say that the radial heat flux is 0. Okay, so Q double prime sub R. And the temperature distribution within the cylinder has the form T, the function of R and Z. So if you look at this as the coordinate system here, we know Z is to the right, so we'll say R is going outward from there. So technically it should look something like that. So maybe we'll go ahead and fix it up here like so. And it gives an equation here, and they give the coefficients. So there's a number of things that need to be found here. First thing you want to do is determine the radius Ri of the cylinder. That's that inner radius of the cylinder. So for A, you're given a bunch of stuff here. You're given that K is equal to 16 watts per meter Kelvin. You're given R sub O is 1 meter. You're given Z sub O is 2.5 meters, or 2 times Z sub O is equal to 5 meters. You're given that the inner surface of the cylinder is insulated, so Q double prime R at Ri is equal to 0. And you're given this temperature distribution T, R, and Z is equal to A plus B R squared plus C times logarithm of R plus dz squared, and you're given all these numbers are. So A here is negative 20 degrees C, B is 150 degrees C per square meter, C is negative 12 degrees C, and D is negative 300 degrees C per square meter. And R and Z are given in meters. So what we're trying to find here is what's the inner radius R sub I. So let's write that down. So to find this, we want to take advantage of the fact that the inner radius is insulated, because we know that if something is insulated, the heat flux is 0. So Q sub R double prime, R sub I. Technically it's R sub I and Z because it's a 2D problem, so we'll write it out more appropriately here. Is equal to negative K dt dr for R and Z, located at R equals R sub I equal to 0. So this tells us then that since you can divide through both sides of this equation by K, the K just goes away because K is going to be non-zero. And also the negative sign as well, dividing through by negative 1. You get TDR at R sub I is essentially equal to 0. So let's find TDR. If you look at the equation for temperature at the top, this tells you then that A, B, C, and D are constants. So if you take the derivative with respect to R, of course A is going to go away because that's a constant. What you get is you get 2 times B times R plus C divided by R, and then a dz squared term. D is a constant, so that doesn't come into play. And then, of course, you have the Z instead of R, so that goes away. So you're left then with this equation here. So we're going to take this derivative of temperature with respect to R at the inner radius R sub I, and we're going to set that equal to 0. So of course what this means then is 2BRI plus C over RI is equal to 0. And we do a little bit of quick algebra here. Let's multiply through both sides by RI. So 2BRI squared plus C equals 0. Therefore we can solve for RI as being then negative C over 2B. So if we plug in the numbers here, C is going to be negative 12 degrees C. And then B is 150 degrees C per square meter. So you plug it all in, what you get is 0.2 meters is your answer. Alright, so what we did now is then we found then the inner radius of the cylinder. Okay, so moving on to part B. Okay, part B, if we go up to the top here, it says obtain an expression for the volumetric rate of heat generation Q dot. And what we're going to do here is there's a couple of different ways we could have done this. We could have essentially followed the rest of the problem. We could have done an energy balance of the whole thing, found the heat flux out both the sides and the ends of the cylinder here, and done an energy balance to figure out Q dot. What we're going to do instead is a little bit more direct, and that's where we're going to apply it into the heat equation. So Q dot, and of course the units are watts per cubic meter. So we're going to take the heat equation for the cylindrical coordinate system, and it looks like this: 1 over R ddr rdtdr plus d squared t z squared plus Q dot over K is equal to 0. So from this, we know the temperature distribution. We can take the appropriate partial derivatives, and then we can solve for Q dot over K. So we know how to do dTdr. We've already done that in the previous problem, but we haven't done anything with d squared t dz squared yet. So if we look at the equation above, we can solve for dt dz fairly easily. The temperature is a function of R and Z. You see the only term here that has a Z in it is the last one, so it's D times Z squared. So of course the derivative of that is going to be 2 times T times Z. And the second derivative then, D squared T dZ squared is equal to just simply 2 times D. So that's easy enough. Go ahead and we'll put that into the above equation here. We already know dTdr, so let's go ahead and modify this thing now. So first let's take Q dot over K and isolate it out on one side. So we get then is minus 1 over R ddr rdtdr minus d squared t dz squared. So we're going to plug in then for dTdr, which we know from the first part of the problem here is going to be 2br plus c over r. And then we're going to plug in for d squared t dz squared, so it's going to be then minus 2 times d. Okay, continuing on here. Multiply these two numbers inside, the r times 2br plus c over r. We get 2br squared plus c. And of course, you can't take the derivative of a constant, so the term with c is going to go away when you take the derivative. We get minus 1 over r times 4br minus 2d. And to finish up here, you're going to get then minus 4b minus 2d. So effectively then, we can then solve for Q dot is equal to minus K times 4b plus 2d. So it's going to be minus 16 watts per meter Kelvin times 4, and then B is 150 degrees C per meter squared, plus 2, and then D is negative 300 degrees C per square meters. So as you can see, you have a plus 600 and then a minus 600, so equals 0. So after all this work here, we get 0 heat generation. So Q dot is 0 watts per cubic meter. Alright, so that's part B. So part C then. Determine the axial distribution of the heat flux at the outer surface, which is Q double prime sub R, located at RO and be a function of Z. So if we want to find this heat flux, then we want to find what the heat rate is at the outer surface and whether or not it's into or out of the cylinder. So we're going to use the same temperature distribution again for part C. So we're going to find the heat flux in the radial direction at RO and Z. And then we're also going to find the heat flow also at RO and Z. So let's find the heat flux. The heat flux we know from part A, in the radial direction, is going to be minus K dTdr. Here we're going to evaluate dTdr at RO. So you already know how to calculate dTdr based on the temperature distribution. That's simply going to be this 2Br plus C over R. And here we're going to evaluate at R equals RO. Let's go ahead and multiply this K through, minus 2KBRO minus CK over RO. So now we can put in numbers. And what we get then is the heat flux at RO and Z is minus 2 times 16 watts per meter Kelvin times B, which is going to be 150 degrees C per square meter, times RO, which is 1 meter, minus C, which is negative 12 degrees C, times K, which is 16 watts per meter Kelvin, divided by RO, which is 1 meter. And the answer to this is minus 4,608 watts per square meter. So now we can find the heat flow, which is simply the heat flux times the surface area associated with the outer radius of the cylinder. So let's write that out here. RO and Z is going to be the heat flux, and RO and Z times this surface area, which we know is going to be 2 pi RO times the length, which is 2ZO. So if we write it out with the appropriate numbers here, we're going to get then negative 4608 watts per meter squared times 2 pi times RO, which is 1 meter, times 2 times ZO, which is 2.5 meters. And the answer we get then is minus 1.448 times 10 to the 5th watts. So let's take a look at the diagram and find out what's the best way to express this. We're saying that we have this is the side view of the cylinder here. We know that R is going out from the center and Z is going to the right. And we're saying that the heat flow in the R direction is negative 4608. So it's a negative number, so we have to turn around and have it pointing in. So we're saying here that the total amount of heat then is going to end up being 144.8 kilowatts coming into the side of the cylinder. And that ends part C. Now part D, you're going to do a similar thing. It says determine the radial distribution of the heat flux at the end faces of the cylinder, which are at plus Z0 and minus Z0. There's actually a mistype here. This should be Q sub Z, Q sub Z, because you're trying to find what are the heat flux out of the end faces. And that's what you would get to look at it appropriately. You're finding the heat flow and heat flux in the Z direction, not the R direction. Then, just like at part C, you're going to find the corresponding heat rates and find out if they're in or out of the cylinder. So just like with part C, we're going to find some heat fluxes. So we're going to find the heat flux at plus Z0 and minus Z0, along with the heat flow rates I know that technically they could be functions of R, but it's pretty clear from what we did earlier on when we found we took the derivative of temperature with respect to Z that there is no R term, so we can just leave it out for now. I think that's okay. So let's first find what's going on at plus Z0. So QZ double prime at plus Z0 is minus K dt dZ evaluated as Z equals Z0. So if we go back to here, we know that dt dz is 2dz. So minus k times 2dz evaluated at z equals plus z0. So we get minus 2kd z0. And if we plug the numbers in, we get minus 2 times 16 watts per meter Kelvin, d, which is minus 300 degrees C per square meter, and then Z0, which is 2.5 meters. So if we do that, we get 24,000 watts per square meter. Okay, and then of course the corresponding heat flow rate is going to be this heat flux times the area, and the area is just simply going to be pi times RO squared minus RI squared. So it's going to be 24,000 watts per square meter times pi times 1 meter squared minus 0.2 meters squared. And our end number from this is 7.24 times 10 to the 4th watts. So let's take a look at this here. Look again at a side view of the cylinder. We're talking about at the location Z0, so it'll be this spot right here, plus Z0. We know that Q sub Z is positive, which tells us that the flow is going to be going in the positive Z direction, like so. And of course the value from looking at the number here is 72.4 watts. So at this end we get 72.4, kilowatts. Out of the cylinder. Now we can do the same thing at Z equals minus Z0. Very similar to what we have up above, right? Because it's just going to be still minus 2kd, and then instead of at Z0, it's going to be minus Z0. So you get the same result. You get 24,000 watts per square meter, except you have an additional negative sign. So this ends up being the minus 24,000 watts per square meter. And then along the same lines, Q sub Z at minus Z0 is going to give you the same number, except it's going to be a negative. So it's going to be minus 72.4 kilowatts. So if we look at that now, we're looking at this edge right here. And since the Q sub Z is now negative, it's going in the negative Z direction. But you notice that because it's going in the negative direction here, it's still going out of the cylinder. So we can say that the heat then is 72.4 kilowatts out of the cylinder. So in both the positive Z0 and negative Z0 ends, you're getting a heat flux out of the cylinder. So now we go to part E. And in part E, we're going to verify that the results are consistent with an overall energy balance on the cylinder. So all the stuff we've done up to this point will pay off. We'll draw our cylinder again. We know from earlier parts that we have 144.8 kilowatts coming in to the radial sides, and we know we have 72.4 kilowatts coming out of the ends, and we know that there's no generation inside. Q dot is 0. So we're going to draw an energy balance then, form an energy balance over a CV we're drawing around the whole cylinder. Get the ECV dt is E dot in minus E dot out plus E dot gen. We know from the problem statement that it's steady state, so that term goes away, and we know that Q dot is 0 that we calculated, so there's no generation. So all that's left then is just plugging in what E dot in and E dot out are. So E dot in we know is 144.8 kilowatts, and then E dot out is going to be 2 times 72.4 kilowatts, which is equal to 0, so therefore everything looks like it's working okay. So this ends problem 249.